In this video, we're going to look at the trigonometry of a 45 degree, 45 degree, 90 degree right triangle. And 45 degree angles in trigonometry, like 30 degree angles and 60 degree angles as well, are important in the study of trigonometry, and we wind up calling them special angles. So 45 degrees is going to be our introduction to the first of three special angles. So what we want to do to develop the trigonometry around 45 degree angles is to start with a 45, 45, 90 degree triangle with legs of length 1. And we want to recognize that because we have a 45 degree angle here and here, we have an isosceles triangle. And when we have an isosceles triangle, side lengths that are adjacent, the angles that are the same lengths, which is why those are both length 1 on this 90 degree triangle. And we also want to recognize that 45 degrees is equivalent to pi over 4 radians. And if you had a hard time thinking about why that's the case, we could just quickly think about, well, 45 degrees, if we think about the upper half plane, is going to break the upper half plane into 4 chunks. So we get 45 degrees plus 45 degrees is our 90 degrees, plus 2 more 45 degrees to get 180 degrees. So to get a quarter of the upper half plane, we would do 180 degrees divided by 4, dividing that upper half plane into 4 equal sized chunks. So if 180 degrees is equivalent to pi radians, in other words, if pi radians is a sweep through the upper half plane of 180 degrees, then we would be dividing pi radians into 4 even chunks. So we could also have labeled the corners here pi over 4, pi over 4, and 90 degrees is the same as a pi over 2 radian angle. So we could have labeled these in radians or degrees. So the first step really in looking at this is to go ahead and orient the 45, 45, 90 triangle a little bit differently. So I'll spin it around, reorient it, and then from this vertex at the 90 degree angle, I'm going to drop a perpendicular to the side opposite. And then I want to notice, once I drop that perpendicular, if I throw away this half of the triangle so that I'm just working with the left hand side from the dropped perpendicular, so this was 45 degrees, now I have a 90 here. Well, this angle up here has to be 45 degrees because the sum of the angles needs to add up to 180. 45 and 45 is 90 plus 90 is 180. Or dropping a perpendicular is, for an isosceles triangle, is actually going to give you an angle bisector up here. So if I just take this left half of the right triangle that I started with, I wind up with this new triangle, and I can think about, well, what is the length of half of the side here? Well, we could figure that out. We had a 90 degree angle here, so this whole length is the hypotenuse of a right triangle, and we know that the square of the hypotenuse is equal to the sum of the squares of the sides, and this is just going to add up to a 2, and so we get h squared equals 2. So if we take the square root of both sides, we would only do the positive square root because this is a length. We'd find that this distance is the square root of 2 all the way across. When we drop the perpendicular here, this actually bisects this side. So half the length, in other words, square root of 2 divided by 2 would be half the distance. So when we throw this away and write this guy here, we know that this is square root of 2 over 2 units long. And because we have an isosceles triangle, we also know that this is the square root of 2 over 2 units long. So it turns out, bottom line is that if we have a 45 degree, 45 degree, 90 degree right triangle, with a hypotenuse of 1, we know that the other two side lengths are going to be square root of 2 over 2 and square root of 2 over 2. And because that's the case, that means that the trigonometric functions on this triangle can be easily defined. So the cosine of 45 degrees, based on our definitions that we've established for the trigonometric functions, is going to be adjacent over hypotenuse, which is just going to be square root of 2 over 2. And that means that the secant is easy to, of 45 degrees is easy to calculate, because secant is the reciprocal of cosine, so we just get 2 over square root of 2 here. And the sine of 45 degrees is going to be side opposite over hypotenuse, which is just going to simplify to square root of 2 over 2. And the reciprocal function for the sine is the cosecant, so the cosecant of 45 degrees will be the reciprocal of this. And again, for my purposes, having the radical in the denominator is okay. We could rationalize the denominator if we had to put this into, say, a online homework platform that wanted only a rational number in the denominator. And then the tangent function is easy to get here as well, because it's going to be the side opposite 45 degrees divided by side adjacent. So we wind up getting root 2 over 2 being divided by root 2 over 2, which is just 1. And that makes the cotangent easy because the reciprocal of 1 is also 1. So on a 45 degree, 90 degree, 45 degree right triangle, the trig functions are well defined. And because we can come up with easy exact answers for the 6 trig functions, we call the angle 45 degrees a special angle, because the side ratios are well defined. Notice, because the side ratios are well defined, we could use similar triangles to find the side lengths of any 45 degree, 90 degree triangle by using similar triangles. So based on what we just established, we know that if we have a 45 degree, 90 degree right triangle with a hypotenuse of 1, we know that the other two legs are going to be root 2 over 2 and root 2 over 2. So if we have any 45, 90 right triangle, we could use similar triangles to find an unknown length. So for example, if I start knowing the length of one of the legs, because I have an isosceles triangle, I automatically know that the other leg adjacent to the 45 degree angle and the 90 degree angle is also going to be length 5. And then I could use similar triangles to calculate the length of this hypotenuse. I could say, hey, the side ratio of hypotenuse to 5, the side ratio of hypotenuse to 5 is going to have to equal, by similar triangles, the side ratio of the hypotenuse, which is 1, 2, the square root of 2 over 2. And when we divide by a ratio, it's the same as multiplying by the reciprocal. So we get 1 times the reciprocal of this, which is going to equal 2 over the square root of 2. And this is h over 5. And then we just multiply both sides by 5. To get 1 times h is h, which is going to equal 5 times 2 over the square root of 2. And then we want to recognize that this can be simplified. In other words, the square root of 2 times the square root of 2 equals 2. Square root times square root gives you square root squared. The squaring cancels the square root, which gives you a 2. So if we take 2 and we divide it by the square root of 2, so divide this by the square root of 2 on both sides, we see that the square root of 2 equals 2 divided by the square root of 2. So we can simplify this to 5 square root of 2. So this is 5 square root of 2 for this length. Here I start with the length of the hypotenuse. If I don't know the length of the other two legs, I do know that I have an isosceles triangle, so I do know that leg 1 equals leg 2. And I know that the side ratio leg 1 over hypotenuse 5 is going to correspond to the side ratio square root of 2 over 2. Here's my leg 1, root 2 over 2 divided by hypotenuse. So leg over hypotenuse equals leg over hypotenuse. But this is just the square root of 2 over 2. So we have leg 1 over 5 and multiply both sides by 5. We get 1 times leg 1 is leg 1 equals 5 root 2 over 2.